Ben Hartkopp. He's the founder and IP and technology manager at Quantica, and he's joining me on the stage, and he'll be telling us about why 3D printing has failed the electronics industry. Again, a very interesting company, and also for those of you who will be joining our Berlin event in October, one of the tours the day before the event, so we organize a series of tours, and one of the tours will be going to Quantica and showing their sort of workshop. So if you're interested, do sign up for that. So welcome on stage, Ben. Delighted to have you here.
Thank you so much for having me. 1 second. Yeah, okay. So my name is Ben Hartkopp. I'm from Quantica, one of the founders, actually. I'm going to be talking a little bit about why 3D printing has failed the electronics industry so far, at scale, let's say, and a look into the potential futures for 3D inkjet, specifically in electronics applications. So a little bit about us. Yeah, I founded Quantica with 2 colleagues in 2018 in Berlin. We now have offices in Barcelona and more than 70 employees. And we basically developed a novel type of 3D inkjet printhead, also, of course, applicable for 2D applications. But yeah, this has been going on since 2018. And we are, with this, enabling our customers to basically print a much wider range of materials. Specifically materials that are much higher viscosity, and that, of course, inkjet allows for multi-material printing, and we are offering systems that are completely open. So there's a lot of process control with our systems, and we've accumulated a couple of very interesting partnerships, as you can see, with XA, Altana, lots to do with Fraunhofer, and also industrial partners such as Real, where we are basically working on new types of applications, and we're bringing out our first commercial offering in Q2 of 2024. So yeah, where is the 3D additively manufactured electronics revolution? I would say it is happening slowly. It's taken hold in certain type of areas with specific application methods, such as aerosol jet. Has been able to create some value for antenna and trace printing on select geometries because they can inherently print at large distances, and direct writing is used for a lot of repair and prototyping. But in general, these offer little value for large scale or cost-effective production, and 3D printed electronics in general have failed to do so, because subtractive production is still the only economically viable choice for large-scale PCB production, for example. So this is, it's very different for different types of methodologies, and not all methods allow for the same freedoms. So especially if you're talking about digital printing, the precise deposition at high resolution, high spatial resolution of functional materials without really affecting the substrate that you're depositing on, such as putting pressure on the substrate during flexographic printing, or requiring high temperatures such as direct metal printing, or not being able to precisely deposit your material in silk screening or spin coating and spray coating, is a big sort of hindrance for having a general technology that enables electronics production. Further, a lot of these are not really scalable. Even the aerosol jet, is able to deposit certain types of traces, but doesn't really allow for inline on continuous deposition of material, and also further does not really allow for multi-material deposition. So the question still remains: is 3D AME at scale possible if there's only really one or maybe two methods that can, have the correct fundamentals with everything. And yeah, these fundamentals include things like multi-material printing, printing substrate and functional electronics components such as traces at the same time. Basically, this allows for a maximum density of function per production resource spent. In order to enable this, you also need a huge range of materials. So that is a huge restrictor, and your material selection depends a lot on its characteristics. So rheological characteristics, curing, and general compatibility characteristics. This has become a very complex task in chemistry to develop any type of functional material sets, especially in